So guys, in the last lecture, we discussed about these independent mechanism. Okay, and corresponding to these independent mechanism, we calculated the collapse load W. Right. So in this lecture, we will be combining these mechanism to get the critical value of the load. Okay. So in this lecture, we are going to discuss about the combined mechanism. And the purpose of combining the mechanism is to get the critical value of the load. Okay. And the concept which we will be using in the combined mechanism is to maximize external work, and minimize internal work. Right. So internal work we will be minimizing by cancelling the cancellation of hinges. Okay, by cancellation of hinges, plastic hinges. Okay, and we will be maximizing the external work by including. We'll combine the mechanism in that way so that the external work done due to maximum external force will contribute to the external virtual work. Suppose here you can see that in the problem there was one horizontal load was acting. Okay, but this horizontal load is not contributing to the work done. Okay, so we'll combine this mechanism with some other mechanism so that this load will also contribute to the work. So that we need to maximize the external work. Right? I hope this point is clear to you. Okay. So now we'll combining the mechanism and see what result we will get. Okay. So basic concept is basically to maximize the external work, right, and minimize the internal work. Okay. So let us suppose this is mechanism 1, this is mechanism 1, this is 2, this is 3, and this is 4. Okay. So first step is to denote some sign to the rotation. Okay. Right. So this, as you can see that this member is rotated in which direction? In anti-clockwise direction, right? Now, the plastic moment will act opposite to this direction. This will be clockwise. Okay. Now in the last lecture, we have discussed that when a moment is producing compression outside, so that rotation will consider positive. And when the moment is producing compression inside, that rotation we will be considering negative. Similarly here, if this moment is producing compression outside, so this rotation will be considering positive. And here this moment is producing compression outside again, so this will be considered positive, right? So here you can see that due to this moment, the compression is inside. Okay, the compression is inside of the frame, right? So we'll be considering theta here. Theta 1 is negative, right? Now coming to this hinge, here you can see that this hinge again there is a rotation in clockwise direction. Okay, so the plastic moment will act opposite to this direction, and that will be anti-clockwise. Okay, so again theta here will be negative because this moment is inducing compression inside. Okay, and what about these points? Here the rotation is in which direction? Anti-clockwise, right? So to balance this, there will be some clockwise movement. Okay, there will be some clockwise movement. So clockwise movement, this situation is like this. This clockwise movement is inducing compression outside. Okay, so this theta will be positive, right? Similarly here, if you see this theta, the rotation is in which direction? Clockwise direction. So the plastic moment will be opposite to this direction, which is anti-clockwise. So again, this moment is producing compression outside. So this theta will also be considering negative. Okay. So I hope this point is clear to you, right? Similarly, let us come to this beam, right? So here you can see that the direction of the rotation is like this, clockwise. Okay. To balance this, there will be some moment in anti-clockwise direction. Okay, so this theta will again be negative, right? Similarly here also, if you see, the direction of the rotation is basically what? Clockwise or anti-clockwise. So moment will be clockwise, right? So again, this is producing compression inside and tension outside. So this will be negative theta, right? Similarly here, this is the direction of the rotation. Here, this is the direction of the rotation. So here you can see that the direction of the rotation is what? In anti-clockwise. So moment will act opposite to this, right? Similarly here, moment will act in anti-clockwise direction. Okay. So this moment will produce compression outside. So this theta we will be considering positive. This is positive, right? I hope this point is clear to you, because this is very important, how to decide the direction, how to give what sign we should use at each rotation. Okay, because we are combining the mechanism and it will be helpful to us. Okay, so here you can see that this member is rotating in which direction? In clockwise direction, right? So to balance, the plastic movement will act opposite to this direction. Okay, so this theta, this will be positive because this moment is producing compression outside. This theta, this rotation is basically what? Anti-clockwise. So to balance this, plastic movement will act opposite to this direction of the rotation. So this will be considering negative, because this is producing compression inside and this is producing compression outside. That's why this is positive, this is negative, right? Similarly, if you come to this point, this is the rotation. Rotation is what? Clockwise. Okay. So again, the moment will be anti-clockwise. Okay. Here, the rotation is clockwise, and the moment will be anti-clockwise. So here the condition is like this. Okay. Right? So this is compression outside, this is compression outside, so this will be positive, and this is compression inside, so this will be negative. Right? Compression outside negative means this, for negative, if this is the column, this portion, this inside portion will be in compression and this outside portion will be in tension for negative. Similarly, for positive, this will be in tension and this will be in compression, right? Now let us come to this point, this thing. Here you can see that the direction of the rotation is basically clockwise. To balance this, there will be some anti-clockwise moment. Okay. So again, this will be positive, right? Similarly here, if you see, this is the direction of the rotation. Okay. So the moment will be opposite to this rotation. This will be again negative. Okay. And here, suppose this line, these two lines are parallel. So here the direction of the rotation is what? Again clockwise. So to balance it, the moment will induce, this is anti-clockwise, so moment will be clockwise. Okay. So this situation is like this. This moment is negative. This is anti-clockwise movement, and here this is clockwise movement. So both movements are producing compression inside. So both the theta will be considering negative here and negative here. Okay. Similarly, if you come to this point, this is clockwise. So to resist, the plastic movement will act opposite to this direction, which is anti-clockwise, right? So this will be considered negative because it is producing compression inside, right? Similarly here, this is the direction of the rotation. which is clockwise. So the plastic moment will act opposite to this direction. So this will be positive. Similarly here, the direction of the rotation is what? Anti-clockwise. So moment will be acting clockwise. So this will be positive, right? So this is how you decide the rotation sign. Decide the sign. Okay. For each rotation, you need to give some sign. Okay. So this is how you decide that thing, right? So here you can see that this was theta 3. This rotation was 2 theta by 3. 2 theta 3 by 3, right? This we have already calculated in the previous lectures, in the last lecture, right? Here this was theta 4. Okay. This is theta 4 again. This was 0.23, 0.24 theta 4. This was 0.43 theta 4. Okay. Similarly, this rotation is 0.43 theta 4 and this is 0.24 theta 4. Okay. This thing we have already calculated in the last lecture, right? And basically these are our theta 1. Here also this is theta 1, theta 1. Okay. So this rotation was theta 2, and this side is theta 2 again, this side is theta 2. So basically both are, if you add this thing, it will be 2 theta 1. So net rotation at this point will be 2 theta 1, here 2 theta 2. Okay. So this is done. So now we will be combining the mechanism. Okay. First, let us combine. First, we need to combine mechanism in such a way that we need to do some cancellation where the cancellation of hinges is possible. Okay. Now, if you combine mechanism 3 and mechanism 2, okay. So combining mechanism 1 and 3. So if you combine mechanism 1 and 3, you can see that here this net rotation at this B point is positive. Net rotation at B is positive, for third mechanism. And here the net rotation is basically at B is negative for first mechanism. Okay. So cancellation of hinges is possible at that point where we have the rotation of opposite sign. Okay. So if you combine these two mechanisms, so at this B point, at B, we will be having this situation theta 1 negative plus 2 theta by 3 is equals to 0. Okay. So from here, we can say that theta 1 is equals to 2 by 3 theta 3. So if you combine the mechanism satisfying this condition, then there will be cancellation of hinges at this B point, right? So now let us combine these things. Okay. So if you combine these mechanism, the plastic hinge at B will cancel out. Okay. If you combine mechanism and mechanism 1 and 3, plastic hinge at B will cancel. Okay. Or you can say that there is no formation of plastic hinge at B, right? And our structure will look like this. This is the case. At B, there is no hinges. So hinges will be at A point, at this point, at this point, and this point, and at this point. Okay. If you combine this mechanism 1 and mechanism 3, right? At B, there will be no hinges. Okay. So now you can see that if you combine these things, now let us calculate what will be the critical value of load is coming. Okay. So let us combining mechanism and mechanism 2, right? So I can write 5.5 MP theta 1 plus this is 10 by 3 MP theta 3. And this is equals to what? This is equals to 6W theta 3 plus 2.25W theta 1. Okay. Now you can see that now we are saying that the plastic hinges is not forming at B. So the work plastic at this point there is no internal work. Okay, so we need to remove that term. So at this point internal work in mechanism 1 was minus MP into theta 1. Why minus sign? Because we are their internal work won't take place. Okay, internal work won't be there because we are cancelling the hinges, cancelling the formation of hinges at B. Similarly, for this wave mechanism, it will be MP into 2 theta by 3, right? So if you solve this thing, it will be 4.5 MP theta 1 and this will be equal plus 8 by 3 MP theta 3 and this is equals to again 6.6 W theta 3 plus 2.25 W theta 1. So now we'll be using this condition theta 1 is equals to 2 by 3 theta 3, right? So 4.5 MP into 2 by 3 theta 3 plus 8 by 3 MP into theta 3 equals to 6 W into theta 3 plus 2.25 W into 2 theta 3 by 3, right? So from here this theta 3 will cancel out each other, okay? And the value, if you solve this thing, the value will be 4.5 into 2 divided by 3 plus 8 divided by 3. 4.5 into 2 divided by 3 plus 8. So this is 17 by 3 MP equals to 6 plus 2.25 into 2 divided by 3. So this is 7.5 W, right? So from here, the W load, critical load comes out to be 17 divided by 3 divided by 7.5. 0.755 MP, okay? 0.755 MP. So if you are combining these two mechanisms, this thing W equals to 0.775 MP. Oh, sorry, if you combine this mechanism 1 and mechanism 3, you are getting this value. W equals to 0.775 MP for mechanism 1 and combining mechanism 1 and 3. Right? Okay. So here you can see that this load is coming. This is not critical load, okay? Because there are loads which is less than this value. This is more. These two loads are more critical than this load. Okay. So generally, what happens is that this collapse load is coming out to be 2.44 MP. So this is maximum. Okay. So we will generally avoid combining those mechanisms in which this is the maximum load. Okay. So we generally avoid this thing. Okay. We don't need to combine. We need not to combine these two mechanisms basically because the critical, this is because in this mechanism the maximum value of the load is coming. Okay, so chances are very less that these two mechanisms, the combining this mechanism and this mechanism will give me the critical value. Okay, I hope this point is clear to you because the critical value of this load is maximum and it is larger than this value. It is much larger than these three values, right? So chances are very less that this combining this mechanism with this mechanism will give me the critical load, right? So now this thing is done. I hope this thing is clear to you. So next thing, is, can we combine mechanism 2 and mechanism 3? If you combine mechanism 2 and mechanism 3, hinges are not cancelling anywhere. Okay, why? Because when you are combining this mechanism 2 and mechanism 3, mechanism 2 and 3, right? So this is our Gable frame, Gable frame. Okay, so when you are combining this these two mechanisms, mechanism 2 and mechanism 3, there will be plastic hinge at this point. It will be there. Similarly, plastic hinge will be there at this point, right? Now, if you are combining these two things, again, the plastic hinge will form at this C point because at C point the plastic hinge is forming in this beam mechanism, right? Similarly, at this point also there will be plastic hinge will add at this point, right? And again, you can see that at this point, because it is, we can only cancel this hinge, right? But it is not possible because here you can see that this theta 2 is negative. Net rotation at this D point. So this is D, this is C. Net rotation at D for mechanism 2 is negative. Okay. Similarly, net rotation at D due to mechanism 3 in mechanism 3 is again, this is negative. Okay, so negative won't cancel each other, right? I already told you previously that if you want to cancel the hinges, it should be positive. Net rotation at D should be positive and they should be negative. Okay, if you want to cancel, but here both the rotations are negative, so you cannot cancel this thing. So hinges, so plastic hinge will be here also. So how many plastic hinges are there? 1, 2, 3, 4, 5, 6. Okay, this won't give me the critical value of the load, because we generally require 4 plastic hinges to collapse. 4 plastic hinges for collapse. Okay, we are not getting any cancellation of hinges here, so we are not combining this mechanism, right? Okay, so now let us come to this. Now combining mechanism 3 and 4. Okay, so if you combine mechanism 3 and 4, what will happen, right? Is there possibility we can cancel the formation of hinges? So if this is the frame, at this point the rotation is net rotation at this point, net rotation at B, net rotation at B in mechanism 3 is what it is positive, right? So this is positive, right? And in mechanism 4, net rotation at B in mechanism 4 is negative, right? So we can cancel. So the cancellation of hinges is possible. Okay. So in this case, and here at this point, if you see at this point, this D point, both the rotations are negative in mechanism 3 and in mechanism 4. So we cannot cancel that rotation. Okay. So ultimately, the plastic hinge will form at this point, this point, and this point. Okay, if you combine mechanism 3 and mechanism 4, the plastic hinge will form at this A point, this C point, this D point, and this E point. Okay, now we will be combining the mechanism 3 and mechanism 4. So if you combine mechanism 3 and mechanism 4, okay, so we cancellation of hinge at B, cancellation of hinge, plastic hinge at B point. Okay, so at plastic hinge, at B point there is no plastic hinge, so the net rotation will be 0. So here the rotation is 2 theta by 3 with positive sign. Here the rotation is 0.43 theta 4. This thing we have already calculated in the last lecture, okay? This member is not rotating, only rotation is in this member. So this rotation is 0.43 theta 4, and this should be equals to 0, right? So from here, what is the relation between theta 3 and theta 4? So this will be theta 3 equals to 0.43 into 3 divided by 2 equals to theta 4. 0.43 to 3. So this is theta 3 is equals to 0.645 theta 4. This is by satisfying this condition, we can there is no plastic hinge at, there will be no plastic hinge at B. If you satisfy this condition, theta 3 equals to theta 0.645 theta 4, then there will be no formation of, then plastic hinge won't form at the B point, right? And these theta and theta 4 are basically virtual displacements, okay, right? So now we'll combine this thing. So this, in this mechanism, this is 10 by 3 MP theta 3, right? From here it will be plus 3.675 MP into theta 4, right? And this will be equals to 6W theta 3 plus 7.0475 W theta 4. Okay. So at B, the plastic hinge is not forming at B. Okay. So we need to reduce that thing, right? So this will be minus MP into 2 theta by 3, because at this point the rotation is 2 theta by 3. Similarly, minus MP into at this point the rotation is 0.43 theta 4. Okay, right? So if you solve this thing, this will be again 8 by 3 MP theta 3, okay, plus 3.675 minus 0.43. So this is 3.245 MP theta 4. Okay. So if you put the value of theta 3, which is 0.645 theta 4, so I can write 6W into 0.645 theta 4 plus 7.0475 W theta 4. Okay. Here also you will put the value of theta 3, which is 0.645 theta 4. Okay. So if you calculate this thing, so this is 4.965 MP, okay, theta 4, and this is equals to 6 into 0.645 plus 7.0475. So this is 10.9175 W theta 4. Okay. So if this is the case, the value of this theta 4 will cancel out each other. So the value comes out to be 4.965 divided by ounce. So this is nothing but the value of W equals to, what should I write? W equals to 0.455 MP. Okay. So you can see that the value of this W value comes out to be 0.455 MP. Okay. 0.4455 MP, 4965 MP is equals to MP theta 4 equals to 10.9175 W theta 4. Okay. So the value of W comes out to be 0.445 MP, which might be critical one. Okay. So if you have this option, in answer, like this 6 option in answer, you can easily mark this thing. Okay. But we cannot say that this is a true collapse load, right? Because for true collapse load, we need to satisfy that yield condition. So we will be checking the yield condition at the critical points. So critical points will be B point. The moment will be maximum. The yield condition we will be checking at this point. Okay. At this point, the moment is there is a plastic hinge. At this point, there is plastic hinge. At this point, there is a plastic hinge. At this point, there is a plastic hinge. Okay. So moment for the yield condition to satisfy, we will be checking moment at this B point, at this F point, and at this G point. Okay. So now the load is acting. This is 1.5 W. This is 0.5 W, right? Here one horizontal load is acting W. Okay. Now basically we will be checking the yield condition at this V point, this F point, and G point. Okay. At this C, D, and E point, we already know the moments. Okay. At this point the plastic moment is acting, right? So now let us first consider this column D. Okay. For D column, the plastic moment is acting in this anti-clockwise direction. Okay, this thing we have already discussed. So this is MP, right? At D point again, the plastic moment will be acting in anti-clockwise direction. So again, this will be MP, right? So at this point, there will be some horizontal reaction. Let us suppose this is HE, and one vertical reaction. Let us suppose this is VE. Okay. So for calculating horizontal reaction, I can write summation MD equals to 0. Okay, moment about D, summation of moment about D, we can consider 0. Okay, or you can say that moment equilibrium about D is 0, right? So if you do this thing, I can write HE into 4. This distance is basically 4. This is 6 meter, right? HE into 4 equals to MP plus MP. Okay, so from here HE will be equals to 0.5 MP, right? So one horizontal reaction is acting, which is of magnitude 0.5 MP in left direction. Okay, so this is okay. Okay. Now we can also calculate the horizontal reaction acting at this point by considering summation H equals to 0 along horizontal direction or x-axis, right? So I can say that W plus 0.5 W equals to 0.5 MP plus, let us suppose horizontal reaction acting at this point is HA. Okay. For equilibrium, horizontal equilibrium, these horizontal reactions, these horizontal loads will be equal to horizontal reactions, right? So if you calculate the value of horizontal, this HA from here, it will be 1.5 into 0.445 minus 0.5. So HA comes out to be 0.1825 MP. Okay, so from HA, from here, HA comes out to be 0.1825 MP. Right? So now, moment yield condition we will be checking at this B point, this F point, and this G point, because these are the point where maximum moment can occur. Moment can occur at these joints at this or at the points where the point load is acting. Okay, so we need to find MB. Let us calculate MB first, right? Consider this column AB. Considering this column AB, for A, the plastic moment will act in this direction, the value of which will be MP. Okay, you can look here. Okay, similarly, let us suppose at this B point, the moment is acting in anti-clockwise direction and the value is MB. Here, this horizontal load is acting, the value is 0.1825 MP. Okay, vertical reaction I am not considering because for MB calculation, for calculating this MB, I don't need any vertical reaction now. Okay, so I can write 0.1825 MP into this distance is 6 into 6 equals to MB plus MP. Okay, from here the value of MB is equals to 0.095 of MP. Okay, so this is less than MP because maximum critical moment for at this B point will be MP. So it is less than MP. So yield condition is satisfied. Yield condition is satisfied at B. Yield condition is satisfied at B. Now we will be checking the yield condition at G point. Okay. Right, so MB is 0.095 MP. Okay, so this is done. Now we will be calculating the checking the moment at G. For calculating the moment at G, we need to have vertical reaction at this point. Okay, so let us consider this portion here. At this point, the 1.5 acting MP will act and it will act in clockwise direction. So this here, this is 1.5 MP at C point. Okay, so this is G point. There is one load, 2W is acting. Here this is 0.5 MP. One vertical reaction will be there. Let us suppose V and then one moment MP. Right. So I can write summation MC equals to summation M at C equals to 0. Okay, to calculate the moment, to calculate this vertical reaction V. So if you do this thing, this distance is 4 meter, this is 3, right? And this complete distance is 6. Okay, so and this is 4. So I can write 0.5 MP into 6 plus 4. 6 plus 4. If you want to calculate moment due to this horizontal force at this point, it will be 0.5 MP into 6 plus 4. And this is clockwise, so I am considering it as positive, right? Plus, due to this 2W load, it will be 2W into 4 and plus 1.5 MP and minus. Due to this VE, their moment at this point will be in anti-clockwise direction. So I can write VE into, this is 4, okay, and minus of MP equals to 0, right? So if you calculate the 10 plus 2 into this is 0.45 VE into, sorry, this is 4 and this is 4. Okay, so VE will be 8. this is 8. Okay. So this VE into 8. So this will be 0.5 into 10 plus 2 into 0.455 into 4 plus 1.5 minus 1 t. So V comes out to be, so this is 1.1425. Let us check it once again. 0.5 into 10. This is 6. This is 4. Okay. Plus 1.5 plus 2 into 0.455 into 4 minus 1 divided by 8. Okay, this is V is 1.1425 MP. Okay, so this is okay. Now we will be calculating moment at G. So for moment at G, the situation will look like this. So this is G point where 2W load is acting, right? At this point, the vertical load is 1.1425 MP. This is 5 meter, right? So this is 4. This is 0.5 MP. This is MP, and this distance is basically 3. Okay. So if you calculate again, moment summation m at G will be equals to 0. So let us suppose at this point the moment is acting in horizontal anti-clockwise direction in G. So I can write mg plus 0.5 MP into this 4 plus 3. This 4 plus 3, which is 7, right? Plus, minus 1.1425 into. So this distance will be again into 4 due to vertical. This is due to vertical load, vertical direction V minus MP equals to 0, right? So from here, this mg comes out to be 2.07 of MP. So you can see that maximum moment capacity which was given in the question is 2 MP for this CD member. Okay, but you can see that this value is exceeding 2. This value is 2 mg. Moment at G is coming out to be 2.07. Okay, so yield condition is not satisfied. Okay, so basically this 0.455 MP is not true collapse load. Is not true collapse load. Okay, right? So there will be some other mechanism which we need to discuss. Okay. So basically here what we calculated, we checked the moment at G, which is it is coming out to be 2.07 MP. But plastic moment capacity of this CD member is basically 2 MP. So it cannot exceed 2 MP. Okay. So for the true collapse load, your yield condition, mechanism condition, and equilibrium condition should be satisfied, right? Here you can see that the yield condition is not satisfied, so that's why this is not the true collapse load. Okay, right? Okay, so now here what is happening is that in this mechanism which we just discussed now, the plastic hinges plastic hinges were forming at this C point, this point, this point, and this point. Okay. So now, and the load which this is coming was equals to 4.55 MPa. Okay, this is the situation. Now we'll check one mechanism in which we will be combining this mechanism. Okay, we will be combining this mechanism with this beam mechanism. Okay, so combining this mechanism. This is Gable mechanism basically, plus this beam mechanism. Why we are doing this basically? Because here the critical load is coming out is very less. Okay, 0.45 MPa. Okay, so what I'm doing is that I'm combining the beam mechanism, and what you can say that for the beam mechanism this load is coming 0.1825. Okay, so what I'll do, I'll combine this mechanism, this minimum value of this critical load, okay, which is not a true collapse load basically. I'm combining this with this beam mechanism 1. Okay, I'm not combining with beam mechanism, sorry, I'm combining with beam mechanism 2, but I'm not combining with it the beam mechanism 1, because for the beam mechanism 1 the collapse load is very high, right? So basically I'm just checking, I need to find the critical collapse. Okay, so that's why this is the less value. Okay, so I'm combining this with this beam mechanism. Okay, so let us see what happens. Okay, so corresponding to this was our equation which we got through. From this thing, principle of virtual work done. Okay, so here you can see that at this point 4 net rotation will be for this mechanism, net rotation at this point will be 0.43 plus 0.24 theta 4. Okay, right? Similarly, at this point, the net rotation is basically all are negative, and this is basically positive. Net rotation at this point is, I need to add these two thetas. Okay, so this will be 0.24 theta 4 plus theta 4. Okay, right. So you can see that if you we can cancel a hinge at C point, right? Because theta 2 at this here is negative, and here is positive. So for the cancellation of hinge, I can write here one condition should satisfy, that is this 0.43 plus 24 is basically 0.67 theta 4 should be equals to theta 2. Okay, or you can say that minus theta 2 is equals to 0. Because if plastic hinge is not forming at C, net rotation at this point C should be 0. Okay, initially the angle between here is 90 degree, so this angle should be again 90 degree. Okay, so if you combine these two mechanisms, the angle between these two members will remain 90 degree, right? Because plastic hinge is not forming. So theta 2 from here is 0.67 theta 4. Okay, so if you combine these two things, if you combine these two mechanisms, right, I can write the equation 6.5 MP theta 2 plus 4.965 MP theta 4, okay, equals to 10.9175 W theta 4 plus 8 W theta 2. Plastic hinge is not forming at C, so we need to cancel the internal work done over there. Okay, no internal work done will be there. So this will be minus 1.5 MP into 0.67 theta 4, again minus 1.5 MP into theta 2. Okay, this is for beam, this is for this Gable mechanism, combined mechanism. Okay, so right? So this is okay. Okay. So now we will be putting this value theta 2 equals to 0.6 theta 4 over here. Okay. So first will be 6.5 minus 6.5 minus 1.5. This is 4.5 into 0.67. 3.35 plus 4.965 minus 1.5 into 0.67. So this is 7.3 MP into theta 4. This is equals to 8 into 0.67 plus 10.9175, 16.2775. So 7.31 divided by ounce. This is equals to, this is coming out to be equals to MP is equals 0.449 MP is equals to W, right? Okay. So the value of what you can say that the value of the collapse load from here is coming out to be 0.44449 MP. Okay. And how we are getting this? What we did over here is that we combined this mechanism which we got through from combining sway plus Gable mechanism. Okay, this is also Gable mechanism, right? With this beam mechanism. Okay, mechanism you can take any independent mechanism. Okay, I can take initially I have taken this as independent mechanism. Okay, this Gable mechanism is independent mechanism, but instead of this I can take this mechanism also. Okay, right? Okay, so this is if instead of this I can take this also independent mechanism, right? There is no problem in that. Okay, I hope you understand this point. Okay, in the initially we have used this as an independent mechanism. Okay, but you can use this as also as independent mechanism. Instead of this, you can calculate collapse load for this also. Okay, then you can combine this with this and get the critical value, right? So I hope this now you are getting this value 0.449 MP equals to W, right? Again, you need to calculate, you need to satisfy the yield condition at. Now, if you do this thing, the plastic hinges will form like this. One plastic hinge will form at this point, one at this point, one at this point, one at this point. Okay, so combining this mechanism with this mechanism, you are getting this condition, right? Okay, so you need to check the yield condition at this C point, this B point, and at this load. Okay, so BFG you need to check, BFC. Okay, guys. So you can check this thing, okay, and see whether this is a true collapse load or not. Okay, I've already discussed how to calculate the yield condition at different points. Okay, right? So basically you can check this and get the value of the true collapse load, right? So basically the true collapse load, if you calculate, if you check this thing, the yield condition will also satisfied and the true collapse load is coming out equal to this. Okay. So I hope this problem is a little bit complicated, this Gable frame problem. It is different that the rectangular frames, right? So I completed this problem. So if you have any doubt regarding this topic, you can write in the comment section. Okay, guys. So basically, the important thing here is to see that this while combining sway plus Gable, the critical value is coming 0.445 MP, and this value we combine with this beam mechanism, and we see and we saw that this value is coming 0.449 MP, which is just equal to this, okay, which is just equal to this, right? So so if you have any doubt, you can write in the comment section. So thank you very much, okay. And this is the important part over here, right? That when we combine this mechanism with this mechanism. Okay guys, thank you very much.